Unit 6, Similarity, Section 3. In this section, we're talking about perimeter, area, and volume of similar figures, and in particular, their scale factors. So if we can find the scale factor of two similar figures using their, side lengths, what would the scale factors of the perimeter be, or the areas, or the volumes be? So we're going to talk a little bit about that. We're going to start with a review, just so we're clear on these definitions. A scale factor, once again, is a ratio between similar figures. Notation for that is K, and we usually do new over the original. So if we're shrinking it, it's going to be a fraction because our new one is going to be a smaller number than our original number. Or if we're blowing it up, the new is going to be bigger, so it's going to be greater than 1 for our scale factor. Perimeter is the distance around a figure. The units for that tend to be things like meters or kilometers or miles or yards or things like that, and they are in one dimension. And so I'm just going to write, it's just plain units. And if we don't know what units we're using, we just say units. And so that's when something is just, how far is it from here to here? One dimension. Or we trace that same line around a shape, and that's just in one dimension. Area is the amount to cover something. So that's when we're thinking about how many tiles is it going to take to cover this floor? How much paint is it going to take to cover that wall? Or how much fabric is it going to take to cover this table? So that's when we're thinking about things in 2 dimensions. And we're thinking about units squared. So how many square feet is this floor? Or how many, acres tend to be something that are like something squared. So you're thinking about in 2 directions. So you think how much this way and how much this way is it going to take to cover this whole thing, however big it is. So it's 2 dimensions. And volume is our last one, and it's amount inside. So that's when we're talking about how do we fill some sort of container. And that's in 3 dimensions because we're thinking about, like if you're picturing like a water glass, you have the bottom circle, and then you have how many circles on top of that are there. So you're thinking about 2 directions in the bottom, and then that 3rd direction going up. And so those are units cubed, So it'll be cubic centimeters or cubic feet or something like that. And so that's 3 dimensions we're thinking about this way. It's kind of hard to draw 3-dimensional things in a 2-dimensional space, but it's like if we had that water glass I was talking about, you'd have this cup, and you'd have to think about the bottom filling that 2-dimensional area and then going all the way up in the cup. Before we do an example, we're going to do a quick side note that's not in your notes. So if you have a little space, I would just write it to the side. This is a conclusion that you'll probably come to later, but I wanted to address it now. So we were talking about scale factors and how that relates in 3 different dimensions. The scale factors are affected in a certain way that gets to be kind of predictable. So if we're first talking about, something in 1 dimension, I'm going to make up a shape. So I'm going to think about, let's say we have a square, and this is our old one, and then I want to blow it up to be something bigger. So let's say this is length, this is width, and then I blew it up 3 times the size. So say 3L and 3W. So 3 times the length, 3 times the width. Okay, in 1 dimension, something that's 1-dimensional would be something like perimeter. So I would just think about perimeter would be, I'm going to do the new over the old, so that'd be 3L plus 3W plus 3L plus 3W. And the old one would be L plus W. I'm just adding up the lengths of all the sides. And I should say, before we even do that, let's find our scale factor. And so we usually do that just by taking similar sides. So I'm just going to do these two sides right here. I'm going to say new 3L over 1L, which I can get rid of both of those L's, so our scale factor is just 3. So we're going to see how these three different dimensions relate to that original scale factor. Okay, back to the perimeter. If I was going to simplify that, I could combine those to be, I have 6L in total and 6W and 2L and 2W. Now I want to try and cancel some things out. So if I took a, let's see, if I took a 3 out of the top, then I could just have 2L plus 2W over 2L plus 2W. So that, I'm going to write it right over here, that will equal just 3, which equals our K. So when we're doing perimeter, the scale factor is just the same as our regular scale factor. Okay, but what if we're doing something in 2 dimensions? So what if I'm finding the area? Well, that's, if we remember, area is length times width. So I'm going to do the new shape first. So I'm going to do 3L times 3W over just length times width. I'm going to combine those just to be 9 length times width over length times width, which I can cancel those out, so I just get 9. And if I look, how is that related to my K? Well, that's actually K squared, which kind of makes sense because we have units squared for area. And so when we think about our scale factors for area and how they're related, we think about K squared. And so I bet you can kind of guess what 3 dimensions might be like. Let's just try it. So let's say I made these into cubes, and I'm not going to draw a new picture, but I want you to think about, you know, this is a cube, and this is a big cube that you can't really see all of it. And say our height is also, so this is just h, and this is 3h. Okay, so we would have, we remember volume is length times width times height. Ugh. So we have 3L times 3W times 3H over L times W times H. So it would be 3 times 3 times 3, which is 27 times length times width times height. And keep in mind, usually when you're solving these problems, you'll have actual numbers, not just length, width, height. I'm just doing that with variables so we can kind of see it's a generalizable case. And we can cancel those out, so we just have 27, which we know to be K, which is 3 cubed. So we're beginning to see how these scale factors relate to one another in relation to the original scale factor and how we're used to finding them. Last thing I want to touch on really quickly is a quick review of exponent rules. It's just been a little while, and I want to make sure we're clear on how those work. So quick reminder, if we have a fraction, a over b, and we want to take that all to the n power, it's like we kind of distribute the power. So we have a to the n over b to the n. So we have to do it to both the top and the bottom. So if we had an example, if I had x over 5 cubed, that would be x cubed over 5 cubed. So 5 times 5, 25 times 5 is 125. So it'd be x cubed over 125. All right. The next thing would be, what if we had a times b to the n? And that, once again, we have to distribute to both of them. So we have a to the n times b to the n. Example, what if I had 3n cubed? Well, that would be 3 cubed times n cubed, which would be 3 times 3 is 9, times 3 is, oh, I don't have my calculator handy, but I'm just going to write 3 cubed, and you can plug that in later if you want. But you get the gist of how that works. Another thing with square roots, or any kind of roots, we can also have cube roots, or the fourth root. all of those, I can go on forever. So if I want to do the square root, let's say, of a fraction, we once again have to do the square root of both parts. So square root of a over square root of b. So example, if I was going to have the square root of 9 over x squared, I'm going to write it down here, I'd have the square root of 9 over square root of x squared, which would be 3 over x. So, like I was saying earlier, since we can have x to any power, if n's any number, we can also have the nth root of any x. So it's not always just the square root. The square root's like something unsquared. So in your calculator, it's the buttons. You can ask me if you're unclear, but it's usually going to look like something like this: x root to the of y, or y to the x power. And so you do the opposite. So if I have something cubed, I'd want to do the cube root. Or if I have something to the fourth, I'd want to do something to the fourth root. So those are a couple review things and reminders. Now we'll move on to the examples in the next video.